Well, thanks for the invitation. It's wonderful to be here, to see such a room full of people, some known faces, to hear about differential privacy. When I was preparing this tutorial, I put myself in the mind of the fellows I know that are around here. So the content is somewhat technical, but I appreciate not everyone is here to learn the maths, but just to get a gist of what differential privacy is about. So I'll do my best to stress intuitions along the way. And please feel free to interrupt at any time. I'm happy to take questions during the talk. I would like this to be like as interactive as possible, in the sense that if you have a question or you don't understand something, don't wait until the end, like stop me right away. So here's the structure of the tutorial. So there's essentially 4 parts. I'll start with a section on which I entitled, "Do we need mathematics to study privacy, like seriously?" And this is meant to give you a motivation, an overview of what differential privacy is about in the whole context of like privacy preserving data analysis. And it's kind of the standard. So if you've seen any other tutorial on differential privacy, we all say use the same example. So you can sleep during that part. The second part is also kind of standard. We'll talk about the definition of differential privacy and its basic properties and some basic building blocks that are usually called mechanisms in differential privacy. The next 2 sections, here's where like you could start talking about like lots of stuff. Differential privacy has been around for over a decade, and there's lots of literature, lots of mechanisms, lots of things we could talk about. So these 2 sections, 3 and 4, are my personal choice based on my personal interests. I'm a scientist, I work on machine learning. So in part 3, I'll talk about differentially private machine learning. And then in part 4, I'll talk about like some variations on the definition of differential privacy. And there's, again, many of those. And I'll basically give you like 2 concentrated differential privacy and local DP, which are like the ones that are more interesting for what I do. OK, so do we need math to study privacy? Really? Unfortunately, we do. Well, I don't know. Not unfortunately for me, I'm a mathematician, so that's a good news for me. But one of the reasons we need to formalize the notion of privacy and we need to come up with formal ways to study it is because we've seen so many fiascos in the past, especially when people try to do anonymization. Right? So in anonymization, somebody has a big data set and they want to release a version of this data set to the public for some purposes so that people can do some data analysis on it. But they're worried because the data in this data set is data about individuals. This might be sensitive data. So you can try to do some anonymization to reveal this, to publish this data in a way that the individuals feel secure and are kind of confident that they won't be de-anonymized. But this has failed over and over again. So like with examples like this article in the New York Times in 2006, where IOL had released a database, a data set with search queries, anonymized search queries, of their users for people to try to improve their search engine, researchers. And then these people went and like managed to de-anonymize like this person by just looking at like queries made by the same individual. And basically like because this person was looking for like shops nearby their home and stuff like this, they managed to say, well, this person must live here. And they went to the house, they knocked, they took a picture. And this is what was in the article, a phase exposed for IOL searcher number 4417749. There are more examples like this. Again, for example, Netflix, before it was a streaming service, it used to send DVDs to your place. And in that time, it was very, very important for Netflix that the recommendations they were giving you and the movies you ordered through the mail were like a good fit for you, because you were paying a fixed price and you could get as many movies as you wanted. So they also put together a data set of like how people were rating the movies that they liked or didn't like in Netflix, tried to anonymize it and publish it online for like researchers, in this case in recommendation systems, to try to improve the recommender system. And that was the Netflix prize. And in this case, Narayan and Zmatikov in 2008 published a paper where they showed that actually you can robustly de-anonymize this data set by correlating like the ratings that people were giving to movies and at what time they were giving them with ratings that IMDb users were posting together with reviews. So they said, well, if you like this movie at Netflix, probably you like that movie at IMDb. You submitted your review at the same time that you put your scoring at Netflix. And by crossing several of these, they managed to identify several people, basically linking IMDb user profiles to Netflix profiles that were supposedly anonymized. And then there's other examples, especially in the domain of health records. So in these two papers, Latanya Sweeney and collaborators managed to de-anonymize data from health records from the Washington state, which is a database that you could actually purchase for $50, and it's supposed to be anonymized, and she de-anonymized several people, I think including the governor of the state at the time. And similar things happen with a genome study where people got very good DNA data, but it was supposedly anonymized, and then again they went ahead and by doing this kind of correlation, like what we see in the IMDb and Netflix case, they managed to de-anonymize people. So in general, from these examples, we can conclude that removing identifiers, like all the identifiers here were removed, but and also applying anonymization heuristics is not usually enough to prevent de-anonymization. So one of the reasons for this is because in most cases, these data sets contain high-dimensional data and with high resolution. And this data is essentially unique for each individual. So if you think that there's a company, and this is the kind of information that's stored in the database of a company, and they want to publish this type of information. So they have employees, and they're going to publish, well, this employee works in London in the IT department. She joined in 2015. This is how much she's earning. This is her birth date. This is the nationality and gender. So they might want to publish this because they want people to see that they, for example, what salaries they're paying, or the government might be required to get that information for some accounting purposes. But the problem is that, if you don't have any side knowledge, that might seem very anonymous to you. But if you know that person, if you work at that company, right? So you know there might be only one Portuguese female that joined the IT department in 2015. So from that, just seeing this table, I could infer the salary of this person. So you can obviously prevent this by reducing the dimensionality of the data and reducing the resolution, doing this, saying, well, instead of London, I'm just going to tell you things about the UK. I'm just going to not tell you which month they joined. I'm going to remove the nationality. I'm going to give you the date of birth with a less resolution. And that might prevent this de-anonymization attack. But it's not clear that it will prevent other de-anonymizations attack. It's in a mathematical sense, I don't know how to prove it. But it's certainly more anonymous. On the other hand, it's less useful, right? So if I'm making a study and I'm trying to determine whether this company pays more or less depending on whether you're based on London or Edinburgh, I won't be able to do this with this new data set, and I could do it with the previous data set. So that illustrates some of the problems with anonymization and some of the challenges that you face when you try to do privacy. So there's going to be a trade-off. There's an essential trade-off between how useful the data is versus how private it is. So that's one of the things that I will try to explain in this tutorial. Differential privacy gives you a way to give very quantitative statements about these trade-offs. But before we give you a formal definition, let's try to manage expectations. What can you expect from something that preserves privacy? And here's a couple of things you cannot expect. So I call them unreasonable privacy expectations. One of them is, as already pointed out, you cannot get privacy for free. If you privatize something, you're going to lose some utility. You're going to lose some accuracy when you do data analysis on this. But at least we can hope to quantify how much we lose. The second, and this is a bit counterintuitive, but it's good to be aware of it, is that you cannot hope for absolute privacy. In the sense that if my data is in no data set at all, that doesn't mean that things about me will not be revealed. Because what I do is probably correlated with what my neighbors do, what my friends do, what my colleagues do, what my family does. So all these things are correlated. Even if all these people I interact with contribute their data to a data set, and somebody says, well, I'm going to run a machine learning algorithm to predict how much people in this neighborhood are spending groceries, that thing might provide an accurate prediction for me, even though I've never contributed data to this data set. So it's a bit naive to expect absolute privacy. So you have to think of privacy as something that is like preserving the things that are inherent to you and nobody else, the things that are really like personal and personal identifiers. On the other hand, what are like reasonable expectations? Well, one reasonable expectation, as I was saying, is to be quantitative, is to offer a knob that allows us to tune privacy versus accuracy loss, to tune this trade-off to a place where like we both feel comfortable, the person doing the analysis and the person contributing the data. Another thing you might hope for is plausible deniability. If I contribute my data to this data set and it's analyzed and the results are revealed, I should always be able to say, no, my data wasn't there. Like what this study says doesn't apply to me, right? At least you would hope that you can get this plausible deniability, especially like say in medical studies and when you start thinking about like applications in insurance and health and so on. And finally, one thing, and this is probably the crux of anonymization, is that you want to prevent targeted attacks. These targeted attacks that can use side knowledge, like try to correlate this database with other things that are out there that other people might know and that might use to attack to perform the anonymization, like in the Netflix IMDb case. So you would like something that limits the information leaked, even if an adversary has arbitrary side knowledge. So I'll try to convince you in this tutorial that differential privacy satisfies these things and a few others. But before we go into the definitions, let's just look at a couple of quotes about what's the promise, what differential privacy promises us. And this I like a lot is from like I think it's the preface or the first chapter of this Dwork and Roth book, which is one of the standard references in differential privacy. And basically say, well, differential privacy describes a promise. Okay, that's good. So somebody's going to promise me something. I like when people promise something, especially when they keep the promise. And the promise is made by a data holder or a curator, okay, so somebody that holds this data set, to a data subject, somebody that contributed this data to this data set and might be worried that like people meddling around with this data set might break their privacy and reveal things about them that they want to keep secret. And the promise is that you will not be affected adversely or otherwise by allowing your data to be used in any study or analysis, no matter what other study data sets or information sources are available. Right? So this last bit is kind of one of the important ones because it's about this potential correlated knowledge that some attacker might have. Differential privacy got a big award last year. So the Gödel Prize for 2017 went to Dwork, McSherry, Nissim, and Smith for the original paper on differential privacy. And here's another two interesting quotes from the citation of the prize. One is kind of encouraging, right? It's differential privacy was carefully constructed to avoid numerous and subtle pitfalls that other attempts at defining privacy have faced. So that's encouraging. It might help these problems, it might solve these problems that we see that anonymization tends to have. And also I want to point out, and that's not going to be the subject of the tutorial, but I think this is interesting to know, is that the intellectual impact of differential privacy has been broad, with influence on the thinking about privacy being noticeable in a huge range of disciplines, ranging from traditional areas of computer science, economics, game theory, false discovery control, official statistics, econometrics, information theory, genomics recently, law and policy, and you name it, okay? So it's kind of it's a very cute, small mathematical definition that seems to like encompass phenomena that appear in many places. And I think that's one of the reasons why it warrants an award like this. Okay, so enough blah, blah, blah. Let's go to the math. Okay, differential privacy. We need to define it. We need some ingredients to cook the definition. The first one is an input space, X. So X, you can think of it as the space of all possible databases that we might want to analyze in a data analysis task. And we assume that this space X is equipped with a symmetric neighboring relation. And in the case of databases, you can think that two databases, X and X prime, are related by this binary relation. If I can go from one database to the other by just removing one person from the database, or replacing one person in the database, or adding one person in the database. The definition, the exact definition depends on the paper, it depends on your application, it depends on like sometimes the kind of math analysis that you want to do, like one plays better than the other. But it's interesting, and I'm going to restrict myself to symmetric neighborhood relations for some technical reason I'll talk about later. So X is the space of databases, and we're going to do some data analysis, and we're going to provide some output. And the output is going to come from some space Y. And on Y, we're going to deal with probabilities, so we need it to be equipped with a sigma algebra of measure events. So we can make Y into a probability space. And then there's one parameter. There's parameter epsilon, which is going to be non-negative. And this is going to be this knob that I was talking about when we were managing expectations. Okay, so here's the definition, 2006. Randomized mechanism, M, that takes something from X and outputs a random variable in Y. That's why it's a randomized mechanism. We say that it's epsilon differentially private if for all possible neighboring inputs, X and X prime related by this symmetric relation, and for all possible sets of outputs, E in Y, we have the following inequality. So remember, M is a randomized mechanism, so I can talk about the probabilities of outputs. So I want to say that the probability of the output of M on database X being in some set E is similar in this notion, so it's less than E to the epsilon, the probability of getting an output in the same set when I change one person in the database, when I run the mechanism on the database X prime. And you have to think of epsilon as being a very small parameter, close to 0, so that then this thing is basically 1 plus epsilon. So like if we had epsilon 0, this would say, well, these two probabilities are like, this probability is less than this one, but because the relation is symmetric, you would say, well, and then like this one is less than this one, so they're the same. And we have like a small epsilon. This allows us for some change in the probabilities, but controlled by this epsilon. Okay? There are other important features about this definition. There's two for alls. So it's a universally quantified definition. And that's important because that means that we're capturing like the worst case that can happen, like for all data sets and for all output sets. It also means, like it has a drawback, which it's going to be very hard to verify this thing algorithmically if you want, because we would have to like enumerate all possible data sets, right? So there's a trade-off between like being very being very strong about what we are promising because it's in the worst case versus like saying something that we will not be able to verify experimentally potentially. I already said it's very important that this algorithm is randomized, so we can talk about probabilities. Mechanisms that are deterministic can have a hard time being private unless they just ignore the data set and output a fixed value. So you really need randomization to make things private. There's the epsilon. And there's this neighboring relation. I said it's symmetric. And the intuition here is that to some extent, this neighboring relation captures what you're protecting, right? If I'm saying that two data sets are neighbors, if I remove one individual, I get one data set to the other, that means that I'm protecting like individual individuals. And so this is what is protected, and this probability, this epsilon captures how much it is protected. Okay, so let's go and build a differentially private mechanism, our first differentially private mechanism. Actually, this was built like way before anybody defined differential privacy. So it's DP before DP. Warner in '65 proposed this thing, the randomized response mechanism, for when people were taking surveys about sensitive things, like whether you like Justin Bieber or not. You might not want to reveal that to everyone, right? You might want to keep this private. So let's suppose that there are n individuals that are answering a survey with one binary question. Do you like Justin Bieber or not? And each individual has a true answer, right? So for individual I, this true answer is xi, is either 0 or 1. Either you like him or you don't. But now when we are going to answer this survey, we're not going to do it like deterministically, and we're not necessarily going to do it truthfully. So what we're going to do is we're going to throw a coin, a biased coin. So and this coin is going to come up heads with probability this strange number here. And if it comes out heads, I'll answer truthfully. So my answer is yi, and that's going to be exactly xi. But if the coin comes up tails, I'm going to lie. So my answer yi is going to be the negation of xi. So if my answer was 1, I'm going to say 0 and other one, and vice versa. So this is randomized response. I'm replying to a survey, like everyone's replying to a survey in a randomized way. And we can denote this mechanism by saying, well, we take like these truthful answers, x1 up to xn. We apply randomized response with parameter epsilon that determines this probability that the coin comes up heads. And then we get as output n responses, y1 up to yn. And it's very easy to see here that this mechanism satisfies this intuition that we had about plausible deniability, right? Because if somebody sees the answers of this survey and they come to me and they say, ha, so you like Justin Bieber, say, no, wait, my coin came up tails. So there's no really a way for them to know which was my true answer, right? And this, like, the Justin Bieber example is a bit silly, but suppose you're asking people, do you earn more than 500K a year? They might not want to answer this truthfully, but if there's some plausible deniability in there, and like they might get motivated to answer if you say, well, but this is like going to help us get an estimate of what's going on. Okay, so my claim is that this randomized response mechanism is epsilon differentially private. So let's go ahead and do some proof of this. And that's just because I'm lazy and I don't want to like put the proof in the slides. So let's take two data sets. Okay, so these are the truthful answers of these n individuals. So we have x and x prime. And we're going to assume that these data sets just differ in one individual. So I'm going to assume that the first n minus 1s are the same and the last differs. It doesn't matter where the difference is, so let's assume it's the nth one. So basically, I have that x n prime. I'm going to assume that this guy has different answer because otherwise, like, the distribution is going to be the same. All right? So then what I have to do? Well, I have to, like, pick a set of possible outputs, right? Which, in this case, is just strings of n bits. And I need to see, and I need to compare two probabilities, right? One is the probability that randomized response with parameter epsilon on input x output something from E. And obviously, the first thing I'm going to do is I'm going to say, well, I'm going to split for all the possible outputs in B, and I'm going to say, yeah, I'm going to look at this probability. And now this guy is basically these y1s up to yn's, and this guy is going to be like a bunch of bits, b1 up to bn. Okay? So because the responses are independent, I can also, so this is sum over b, and then I'm going to just say that I can look at each response individually. So this is the probability that yi equals bi. Okay? So now let's look at what happens when we have a neighboring data set. Okay? So if we have, if we say that when I get x prime, I get outputs y1 prime up to yn prime, right? The distribution of the first n minus 1s is not changing because the answers haven't changed. So for I equal 1 to n minus 1, these guys don't change. They're the same. Now, for the last one, it might change, right? So what we have to do is look at what's the probability that yn equals bn. And I'm going to compare this with the probability that yn prime equals bn. And here is where I want to plug these formulas, right? So I answer truthfully with this probability, and I answer falsely with this probability. So I have to consider two cases, right? I can consider the case where bn is the true answer, in which case this guy is gonna have output this thing with probability, with the probability that the coin comes up heads. And this guy, because I'm assuming that this guy changed, is going to have like 1 over 1 plus e to the epsilon. So I can actually remove the 1 plus 1 e to the epsilon, and that's a 1 there. So that's what you get. And in the other case, well, it's the other way around. if Bn was equal to the answer of the guy in the database X prime. So, and if you look at these two guys, this is bigger than this. So I can basically say that this is e to the epsilon. Is at most e to the epsilon. So when I plug this observation that these n minus 1 guys are the same, and for this one I have this inequality, all I'm saying is that I'm changing one and the others remain the same, so I get exactly the same expression for the y primes. And that's exactly what I needed to get differential privacy, because that's randomized response on x prime being in E. Yeah, and I apologize for the people who are that far out, but I'll try to leave this on, and so you can come, for example, take a picture during the break. Okay, so that's the proof. One interesting thing about this proof is that it shows that actually, even though the quantification is over events, I can always get away with just looking at individual outputs. That's going to be important later. So what's this mechanism good for? What can we do with it? One thing we can do is take these answers, take these privatized answers, these differentially private answers, and try to compute the average of the xi's, right? Now, because we've done this like funny stuff with the probabilities, the yi's are actually like biased, so their expectation is not xi. But because you know the distribution, you can unbias them. So you can get, from these yi's, you can get yi tildes that are unbiased estimates of the xi's. And you can average those and compare them to the average of what's the fraction or the average number of people in the population that like Justin Bieber. And if you do this and you apply like a Chernoff bound, you can show that with high probability, this answer that is an average of private things and is going to be private, and if you don't see it immediately, I'll tell you why in a minute, satisfies this bound. Okay, so we have this distance with high probability is bounded by something that's like 1 over epsilon square root n. And that's interesting because that's the kind of thing that I was interested in at the beginning, these very precise trade-offs between utility and privacy. Right? So this bound says, if you keep n fixed and you make epsilon small, you require more and more privacy, this thing blows up, so you get no utility. You get more privacy, but like your accuracy is destroyed. On the other hand, if you keep epsilon fixed, you say, well, that's the level of privacy you feel comfortable with, and you convince more and more people to answer your silly survey about Justin Bieber, then this n grows up and this error goes down. So for a fixed privacy target, getting more and more data about people increases your accuracy. Right? So, sure.
Is this bound should be the expectation or the absolute value?
It's with high probability. Yeah, so you can put a logarithm 1 over delta there if you want. Yeah. Okay, but do we really need to do all this complicated stuff if all we're interested in is computing this average, the average of the answers? And the answer is no, assuming that you are comfortable of being in a slightly different setup, right? And here's where we go into the second mechanism that is like one of the foundations of differential privacy, is the Laplace mechanism, in this case for computing a mean. So how can we go about doing a private mean computation? Well, let's assume we're in a slightly different setting. So a curator, which is somebody we trust, has already collected our answers of whether we like answers of many people of whether they like or not Justin Bieber. Okay, so these are the xi's from before. So again, we have n individuals, but now a curator holds the truthful answers. And all the curator wants to do is basically compute this average number of people in the population that likes Justin Bieber, and release an answer that is going to be private. And private means that by looking at the answer, nobody will be able to determine if like one person in this database liked or doesn't like Justin Bieber, right? Because it could be that I'm the only one that I like Justin Bieber and everybody else doesn't. So if you were just releasing this average, you could say, well, if the average is 0, Borja wasn't in the data set. But if the average is not 0, Borja was in the data set because he's the only one who likes Justin Bieber. And that's a randomized response. So what can the curator do? Well, the curator can obviously compute this average of the xi's, and then it's going to add some noise to it. And in this case, the noise will come from a Laplace mechanism. So we'll sample z from a Laplace with parameter 1 over epsilon n, and we will reveal this noisy answer, this mu tilde, which is the true average plus this random noise. Okay, and for further reference, we'll call this mechanism mlab. So mlab takes x1 up to xn and outputs this noisy average. And again, I was planning to do the proof. I think in interest of time, I won't do it all of it, but there's just one thing that is going to be convenient to recall, which is the density of the Laplace distribution. Okay, so the density of a Laplace distribution with parameter b and mean 0 for a certain output y is 1 over 2b e to the minus absolute value of y divided by b. So if you do all this story again, and that's basically what you need to do, with the difference that instead of like summations, now you have an integral because your output space is continuous, you'll see that basically all this boils down is to saying, well, I have to compute this quotient, which is y minus the average of the xi's divided by b, and the parameter b is epsilon n, so I have an epsilon n here. And I have to compare what happens when I change one point in the data set, right? So I'll have to take the quotient with y, and then I'll have 1 minus n, and I'll have x1 up to xn minus 1 added, and then I'll have an xn prime that's going to be different, epsilon n. So if you look at this quotient, right, what's going to happen is that you can take this guy upstairs, so make it a single e to the something. This guy is common, and you'll have the difference between this guy and this guy. And it's not hard to see that the difference between this guy and this guy, because I only change 1, is 1 over n. So this n is going to cancel with this n, and you will see that this is e less than e to the epsilon. And then you can do the same thing here, right? So you'll have like an event, you'll have an integral of the event, you look at the density, which is like this thing in this case, and you get the same bound. So that's how you show that Laplace mechanism is differentially private, is epsilon differentially private. Now, an interesting thing that happens is that if I compare the utility, right, the accuracy that I was getting for the mean computation in the previous slide with the randomized response, versus what I'm getting with the Laplace mechanism, this looks much better. So again, you can show that with high probability, this difference in the means is now 1 over epsilon again, but now I have an n here instead of a square root n. So this is much better. As I get more and more people to contribute to this data set that the curator holds, the error goes down much faster. On the other hand, I need somebody that I trust to keep all the data, right? It's not like in the randomized response where before I was submitting my answer, I was already randomizing. And we'll get back to this at the very end of the talk. So for now, what I want to say is that sometimes this definition of epsilon differential privacy is not enough. So there are cases where you cannot achieve this, and you have to settle for an approximation. And then is when we talk about approximate differential privacy. So this is also kind of a standard definition, and the only difference is that now we have two privacy parameters, epsilon, which is still non-negative, and delta, which is supposed to be 0 and 1. And it's a probability. Delta is a probability. So this is the definition of approximate differential privacy, and there's just like one difference with the previous one. Now, instead of saying that the mechanism, a randomized mechanism from x to y is epsilon differentially private, now I'm talking about epsilon delta differentially private, and the rest reads the same except for the inequality, where I have this additional slack delta here. Okay? And as I said, that's important because in some cases you cannot get away with delta 0, which is the previous definition. And the intuition is that delta accounts for some bad events that will might have high privacy losses, might compromise the privacy completely, but that we can control with the delta. So if we make the delta very, very small, these things are very unlikely to happen. So how small should delta be? Very, very small, in the following sense. So consider this mechanism. I give you the answers, x1 up to xn of some people, and the mechanism takes a uniform number between 1 and n, and outputs the corresponding response. That's obviously not private. Like every time you run it, it's going to reveal somebody's data. However, it is very easy to see that this mechanism is 0, 1 over n differentially private. So that's just a warning that if you're thinking of working with epsilon delta differential privacy, you should take delta to be much smaller than 1 over the number of individuals in your data set. Because otherwise, this silly mechanism satisfies the definition, and this is obviously non-private. Okay, so why do we have to deal with this business? One of the reasons is because you don't always want to add Laplace noise. Sometimes you want to add other types of noise, like Gaussian. And this leads me to this family of mechanisms. And as you'll see, as we go over and over the talk, I'll try to say, well, this mechanism that we looked at before is part of a bigger family, and this family is part of a even bigger family, and so on. So this is the first generalization in this direction. And basically what I want to say here is that the Laplace mechanism is an example of a more general class of mechanisms called output perturbation mechanisms. And the idea is very simple. The idea is you have, what you want to do as a data analyst is there's a function that takes as input a data set and outputs a vector, a d-dimensional vector. And this can be like computing the average of things. This can be, I want to train a machine learning model on X and output the parameters of the model. It can be anything. So F represents the thing that the data analyst wants to do. And the goal is to see how we can take these arbitrary data analysis procedures and make them differentially private. And to do this, one way is to do output perturbation. So in output perturbation, what you do is you say, okay, I have this F that I want to compute privately, so I'm going to define the global sensitivity, which is how much F can change when I change one individual in the data set, right? So that's the supremum over neighboring data sets X and X prime of the norm of Fx minus Fx prime, and I'm saying delta P because I'm taking a P norm here. And P obviously is not going to be like some weird thing, usually it's 1 or 2, but I'll write it as global sensitivity with respect to the LP norm. So using this definition, what we can hope for is to do output perturbation, which is I'm going to do F, I'm going to compute what I want to compute on my data set, and then I'm going to add some noise, and the noise is going to depend on this delta. And this is exactly what we did with the Laplace mechanism. We were computing an average, and then we added some noise that had a parameter n in it that was actually 1 over the global sensitivity. So in general, an output perturbation looks like this. A curator holds one vector. Well, this is in RD, but it could be a different D than this one. So one vector for each individual, and there's n individuals. And you want to compute this function, f of x1 up to xn on the data. And once you've computed it, you're going to sample some noise. So two examples here are the Laplace mechanism, where you calibrate the noise to be the L1 sensitivity divided by epsilon, and you take DIID copies. This is the output dimension. Or you can do it with a Gaussian. So instead of the Laplace distribution, you take the Gaussian distribution. You take again DIID, zero mean and variance sigma squared Gaussian random variables, where sigma is again calibrated to the L2 sensitivity in this case over epsilon. So this epsilon appears in both cases. And then here you have a delta. And here, and this is a constant. And here the delta is really because if you want to do Gaussian perturbations, you really need to do epsilon delta. You cannot do epsilon differential privacy. So once you have this noise, what the curator does is reveals f plus z, and you can show that, that this is epsilon differentially private with the same proof I sketched here. And for the Gaussian case, I'll do the proof later if there's time. This one I did on the slide, so I'm not afraid to do it. And note that this Laplace mechanism that I provided you in the previous slide is an output perturbation for computation of the mean. Okay, so this, I've shown you like two definitions, three mechanisms. Where's this going? Well, this is going to, now I've shown you that dp is something very formal, is something very specific. There are some instances of it. How do we build more instances of mechanisms? Well, we can compose mechanisms, we can combine mechanisms. So differential privacy offers you a lot of ways in which you can combine things and compute the new epsilon and delta if you combine two mechanisms, for example. So these are the fundamental properties of differential privacy. And as you'll see, like, these are very interesting stuff. This is something that you would really want in any reasonable definition or formal definition of privacy. First one is that differential privacy is robust to post-processing. So if you have a mechanism, which is epsilon delta dp, and you take the output of this mechanism and apply some f to it, doesn't matter if f is randomized or deterministic, this composition is again epsilon delta differentially private. So if I release something and then somebody does something with this differentially private output and releases it again, like nobody loses anything in terms of privacy. Composition, right? So you can also think that you want to run several mechanisms on the same data. So if you have M1 up to Mk, which with their privacy parameters, and then you think, well, I have this data set, and I'm going to reveal the answers provided by M1, M2 up to Mk on this same data set, then you can show that the output satisfies differentially private with the sum of the parameters in the epsilons and the deltas. So when these things are all the same, you get k epsilon and k delta. Now, this is the simple composition. This is very easy to prove, but it's not the best you can do in this scenario. So there's something called the advanced composition theorem, which is in the homogeneous case, it basically says the same. So if you have like k mechanisms, they're all epsilon delta differentially private, and you look at the composition of them, then really what you're getting, the guarantee that you're getting, is slightly better. And this might look a bit scary, right? But if you think epsilon is very small, this guy is like epsilon squared, and this guy is like epsilon, so we can forget about this guy. And this guy is epsilon square root k, whereas here I had epsilon k. So the advanced composition gives me a gain of square root in terms of the first parameter, the important one. And the second one stays the same, the delta. And there's some delta prime that you can use to trade off these two things, so that you actually need to make this thing appear. Group privacy. Group privacy. Sometimes, if you have like say for example, that somebody, instead of contributing one record to the database, everyone contributes T records, right? So the original definition is basically says, I want to satisfy this constraint when you change one record in the database. But if a person is contributing T records, when they get in or out of the database, they affect T records. So they wouldn't be necessarily protected by this original definition. Fortunately, we have the group privacy property that says that if you have a mechanism that is epsilon delta dp with respect to changing one record, and then you look at a neighboring relation that is like you can change T records, then this thing is T epsilon and T delta differential private. So you can very easily do these calculations. And finally, another property that is not super related to composition, but that formalizes this thing that the attacker can have arbitrary side knowledge, is that basically if an attacker models this knowledge as a prior on the data of individual I, right? So the attacker has a prior p prior of xi, and then the attacker observes the output of this mechanism, mx, that is epsilon dp, and uses this output to compute a posterior using Bayes' rule, for example. No, for example, not like Bayes' rule. Then you can show that the statistical distance between the prior and the posterior, which is kind of a way to measure how much knowledge the adversary gained, is basically bounded by epsilon. Okay? So releasing something that is epsilon differentially private only gives an epsilon edge to any adversary that already knew whatever they knew about that person. So that protects against, is a way to formalize protection against adversaries with psi knowledge. Okay, so now we can do another jump, another abstraction. I want to say here that the Laplace and the Gaussian mechanisms that do output perturbation are actually examples of a even more general class of mechanisms, the exponential mechanisms. So to motivate this, you can try to look at what are the output densities, the densities of this output perturbation with Laplace or Gaussian noise. And basically, like removing normalizing constants and so on, you can see that the output density of output perturbation with Laplace is something that looks like this. So y's that are closer to the fx that I wanted to compute have more probability, and y's that are further away have a smaller probability. And here we have the sensitivities and the epsilon parameter. And a similar thing happens with the Gaussian mechanism, but now instead of an L1 norm, I have an L2 norm. So, but basically what you see is that these two densities are saying, I want to give more probability to things that are close to the fx, so that's good. That means that these mechanisms are going to have like good utility in a sense. They're going to prefer things that are close to the original thing. But also there's this like epsilon and sensitivities that kind of like, if you know the Gibbs analogy, these are like temperatures, and they tell you, well, like how likely you are to move away from what you're trying to output depending on the privacy that you require. So these are basically two examples of what we call the exponential mechanism. So in the exponential mechanism, you have something that is not necessarily induced to mechanisms, which is a prior. So you say, well, I have a prior over my outputs pi. Well, a prior that has density pi. And this says, well, I prefer outputs that are small to outputs that are big, but it's something that is data independent. You fix ahead of time. And then when you see the data set, you have a scoring function that, given the data set, will provide a score for every possible output, right? And these are what these like f and the norm are doing in here. So Q will say, well, if you observe this data set, I like this output more, I like this output less. And then you can try to output something sampled from distribution that encompasses these two objects. So the exponential mechanism with prior pi and scoring function q will output a y with density proportional to the prior times exponential of minus beta, and this beta is what you have to tune, times the quality of possible answers. And so these are two examples of this. So the interesting thing is that here I had norms, so I was forced to talk about like real vectors as outputs and so on. Here I've completely abstracted this thing, so y now the output space y can be anything, right? All you need to come up is with a way to say, well, I prefer this answer over this other, and by this much. So what are the guarantees of the exponential mechanism? How we calibrate the noise? So there's one calibration that is very easy, which was in this 2007 paper by McSherry and Talwar, which gives you epsilon dp, and basically says you need to take beta to be epsilon over delta, where this delta is the sensitivity of Q. Defined as, you look at all pairs of neighboring databases, and then you look at all possible outputs, and you want that the quality of each output, when I change one guy in the data set, doesn't change by at most delta. So if this delta is finite, you can get epsilon zero differential privacy, or epsilon differential privacy, with this calibration, and the proof is exactly the same as the Laplace mechanism.
Sorry, I might have missed it. Could you define again this relation x close to x prime?
Yes, so this relation is given to you as input when you're trying to do differential privacy. And And in the definition, I was assuming it's kind of an abstract relation. I was only assuming it's symmetric. But typically what happens is that if you have, I think I actually have it here. So if you have X as a database with data about individual 1, individual 2, up to individual n, then this is related to X prime if X prime contains all the same individuals except 1. So this guy, this is the data from another person, and this is the data from the same person up to the index n minus 1. You're only changing the data about one person. Yes, I mean, like these are not necessarily real numbers, right? These are like from X, which can be anything. It can be R to the D, but it can be other stuff. It's just one record in a database.
When you want like a more general notion of distance between X and X prime, you have these relations.
I don't have a notion of distance. I just have a notion that says you are related to this one, like 0, 1. Like you could say, well, Hamming distance, they're related if they're at Hamming distance 1, for example.
This could be an arbitrary event, right? So something that happens here and doesn't happen there.
Yes. I mean, the typical thing is like you remove one record or you replace one record, but it will depend on your application, right? If you're doing like location data, like you might want to do it different, like somebody moves by this at margin or something like this. Okay, so that's the original exponential mechanism, and then in 2016, Minami Row, in this, like, I really like this NIPS paper a lot. They showed that actually you don't need this bounded sensitivity assumption to make the exponential mechanism work. You can get away with a weaker condition. You can get away with the Lipschitz condition that basically says you look at all possible data sets, neighboring data sets, and then you look at how much you change for one output, and then for another output, and this should satisfy this Lipschitz condition. And this is much weaker than this thing here. So if you satisfy this Lipschitz assumption, and in addition, your Q is convex. So in this case, in their analysis, the output has to be an Euclidean space, but it doesn't. I think you can extend the proof, but that's another story. And your prior is strongly log concave, so that's a kind of a strong requirement on the prior, but it's not so strange because, for example, a Gaussian prior would satisfy this. So the prior is strongly log concave if the density is e to the minus a strongly convex function. So if you have these two assumptions, then you can get epsilon delta differential privacy with the exponential mechanism by taking beta to be this expression, which again has epsilon and kind of L over a square root of the strongly convex parameter plays the notion of delta.
Can you go back to the one slide?
Yeah.
So you call this pi as prior. So then the right exponential is something like likelihood, right?
Yes.
And then the density on the left is then the posterior of x or y?
Yes.
Posterior of x.
Posterior of y.
Posterior or, but true.
Yeah. So as an interesting exercise, you can try to apply the Minami et al. Result to show that the exponential mechanism is epsilon delta differentially private. I think it's a fun exercise. Okay, so we've been in here for an hour. Maybe it's a good time to stop, take a break, and start in 15 minutes again. Cool. Okay, so far we've talked, sorry to interrupt. We've talked about what it means really to talk about privacy in a formal way. What is the promise of differential privacy? How is it defined? How we can define basic mechanisms and how we can compose different mechanisms. And now it's time to do something interesting with these tools. One interesting thing you can do is design differentially private machine learning algorithms. So you have to think, like if you want to do this, the first thing you have to do is think that a whole machine learning algorithm is one query you want to run, right? There's a data set, and one query is, I want to train a logistic regression with these and such parameters and so on, and out come the parameters of the logistic regression model. So once you have thought about it like this, what you could do is you could try to come up with a differentially private mechanism for this by saying output perturbation. And that's one way to do it, and there are other ways to do it. And what I want to do now is talk about two machine learning problems or two approaches to machine learning and how you can make them private. The first is empirical risk minimization, and the other is Bayesian learning. So I'm assuming not everybody is familiar with machine learning or empirical risk minimization. So just to recall, in this setup, we have a curator again that has data. And this data, I call it Z now, is a list of pairs. So for each individual, we have an X, which is a list of features, and a Y that is a label that we would like to predict. So following with the previous example, you could have an X that says, well, this person is this age, this person lives in some place, this person went to this high school, and the label might be whether they like or not Justin Bieber. Right? I mean, everybody wants a machine learning model to predict whether individuals like or not Justin Bieber, it's obvious. So what the curator wants to do, this query that the curator wants to run, is to use this data set Z and perform what we call empirical risk minimization, which is find a parameter vector theta in a space of parameters capital theta that minimizes what we call the empirical risk, or in this case, a regularized empirical risk. So the empirical risk says if you have data Z and you've picked parameter theta, your risk or your error is the average of the error that theta has on each particular XY pair. And then sometimes we have a regularizer R that says, well, I prefer these thetas over these other thetas, so I'll put this knowledge in this regularizer here. And many machine learning algorithms follow this paradigm. So I mentioned logistic regression, support vector machines, linear regression, deep learning, like almost everything in machine learning that is frequentistic and is supervised can be solved with empirical risk minimization. So if the goal is to output the minimizer, so we want to minimize this over theta, one way that we can make this private is to say, okay, I'm going to do my minimization, so I'm going to find the theta hat that minimizes this thing, and then I'm going to do output perturbation. I'm going to add some noise to it. So if I want to do this in a way that I can guarantee is differentially private, I'll need to look at what's the global sensitivity of this guy here. And this can be like very tricky sometimes. So for this reason, people have come up with other ways to achieve differential privacy for empirical risk minimization. One of them is objective perturbation. So in objective perturbation, instead of solving the optimization and adding noise, we add noise to the optimization and then solve it. So this is basically saying that I'm going to take the original risk or loss, and I'm going to add this term here that is going to be the inner product between theta and some random noise. And that is kind of a random regularizer that you can add in here, and it makes the optimization problem random. And you can show that if you pick this Z in a proper way, then the output of minimizing this satisfies differential privacy. Now these two, I mean, I've said this can be hard to analyze, and this can be hard to analyze as well. So another thing that you can do is say, what I'm going to do is I'm going to modify the optimizer, and I'm going to do what you can call gradient perturbation. So in gradient perturbation, what you do is you say, well, I want to minimize this in a way that is differentially private. So what I'm going to do is I'm going to fix an algorithm to minimize this. So now it's not anymore about ERM itself. It's about a particular optimization algorithm to solve ERM. And I'm going to modify the algorithm, make it randomized. And one way to do it, if you know anything about machine learning, you'll probably know that a typical way to solve this is using stochastic gradient descent with mini-batches, which is an iterative algorithm that does gradient descent with, instead of looking at all the data, subsamples of the data at every point, at every time step. And what you can do is you can add noise to those gradients. So at each iteration, you can add noise to make the gradients kind of differentially private. And by composition, the output, because it's obtained by a sequence of differentially private gradients, the output will be differentially private. And then all you need to do to calibrate this thing is to compute how much the gradients change. And it turns out that it's much easier to compute how much the gradients change than to compute how much the output changes or how much the output changes when you perturb the objective randomly. Yeah.
So then your function, f, is the function that transforms the previous gradient into the next gradient. And for that is for what you look at the sensitivity?
You look at the sensitivity of so the only points, the only steps in the algorithm where you touch the data is when you compute the gradients. So you make these computations of the gradient differentially private with some parameter, and then you apply composition to say I'm computing several of those, and that makes the algorithm differentially private.
There's nothing more to it than just composition of this?
Yeah, I mean, yeah, there's nothing more to it. I mean, you have to do fancy compositions to get good rates, like the rates here. But yeah, conceptually, there's nothing more to it.
What I meant is, so there's something more than standard composition. It's non-standard in the sense that it applies only to that kind of problem.
Yes.
How do we split epsilons here? It depends on the algorithm.
It depends on the algorithm. I'm not going to give you an analysis. We could be here for an hour if we wanted to do a detailed analysis of one DP SGD. So, but this is a summary of stuff that you can find in the literature. So I'm listing here what type of perturbation we're using, objective, output, or gradient. What the results assume. So sometimes the results assume that you solve the optimization exactly. But sometimes the results assume that you're actually using an actual, so apply to an actual optimization algorithm. Some of the results are epsilon delta, and some are epsilon, and then you need to make some assumptions on the model. And I'm listing here only results for convex problems. And the reason is because for convex problems, we know a lot about gradient descent and ERM and the solutions that we can get. And in those cases are the ones in which we can quantify the excess risk. So the excess risk is the prediction error, is the error, as the difference in prediction errors between running the algorithm without differential privacy versus running it with differential privacy. So is the equivalent to that 1 over epsilon n that I had in the Laplace mechanism, or 1 over epsilon square root n that I had in the randomized response. So it's a measure of utility. It's a measure of how much prediction power you lose by requiring the output to be differentially private. So what we see here is basically that if we assume that the model is linear and we assume convexity, then with objective perturbation, we get excess risk 1 over epsilon square root n, some hidden logarithmic factors. But with output perturbation, we get the same. And this is exactly the same thing that you can prove even if you assume that you're using an actual optimization algorithm, not that you solve the optimization exactly. So this is this result here. And then what this paper shows is that if you make a slightly stronger assumption, you move from convexity to strong convexity, then you can move the square root n to n. So that's better. So you have something that is easier to optimize, and in addition, you get better utility. So your excess risk is smaller. And this is one of the first papers that considered this perturbation of the gradients. And under, again, these two assumptions, without linearity now, we're just assuming convexity or strong convexity. In this case, we get the square root d here, which is better than this thing, even without strong convexity. And if now we impose a strong convexity, we get a square here. So when this thing is small, this thing becomes even smaller. D is the dimension of the output, is the number of parameters of the model. Sorry, yeah, I didn't define that. O tilde, this is just a way to say that there's some logarithmic factors hidden in here. So there might be a log n here, but the square root dominates.
For SGD, the risk is for each parameter. So for the function, we should multiply to number of the parameters?
This excess risk is in terms of prediction power, is in terms of expected loss.
Because in SGD, we apply the differential privacy on each parameter, yes? Separately.
Not necessarily. I mean, if you're doing Gaussian perturbations, you're always doing the parameters separately because the coordinates are of your noise are IID. But you analyze it all together. And there's further results in the literature. So Abadi et al. Give like an SGD that is differential private for deep learning. I'm not including it here because the optimization is non-convex, so you cannot quantify the excess risk. And the Talwar et al. Paper gives like more detailed excess risk bounds when you have like extra assumptions on the geometry of your parameter space.
So this assumes n iterations of SGD? I don't see the number of the iterations anywhere, so I assume it's n.
No. Like here, like SGD with the number of iterations that is tuned to. So you get this bound when you pick a particular setting of the number of iterations. So if you go to the paper, they'll tell you SGD with this number of iterations satisfies this thing.
I'm a bit confused what your trend model here, what you're trying to predict. Is it like the original data, the value of theta, the gradient?
Yeah, so the setup is this. The curator has data for a supervised learning problem from many individuals and wants to release the model, which is the theta that will result from optimizing this thing in a differentially private way. So if this theta, so if this capital theta, the parameter space is a subset of RD, these are the excess risks that you get. Yeah.
One last question. So which one of these results also satisfy that every intermediate gradient is differentially private, and which ones don't? Do all of these satisfy this?
The ones that are gradient perturbation satisfy this. The others, not. But don't quote me on that, though it's on video. But that's what I remember. But yeah. Okay, so the other paradigm, so ERM is like the go-to thing for frequentist machine learners. So the other approach to machine learning, or the other major approach, is Bayesian machine learning. And in this case, like the setting is exactly the same. There's a curator that has data about n individuals, and they want to do a Bayesian analysis. So they have a prior about these parameters of the model that they're trying to learn. And this prior is P prior of theta. And then there's a model that tells you for a fixed parameter what is the probability or the likelihood of each of these observations that you have. And basically what the curator wants to do is take this data set and compute the posterior, right? That's what Bayesian analysis is all about, and Bayesian machine learning as well. So we want a posterior that tells us these are the likely parameters when we've observed this data under the prior and the model. But obviously, you cannot release the posterior directly. This might be a high-dimensional object and might not be private. So one way to obtain differentially private Bayesian learning algorithms is to say, well, the curator is going to compute this posterior. Let's assume they can do it exactly. I mean, that might not be the case in a lot of practical applications, but let's assume we can compute the posterior exactly. And then what they're going to do is they're going to take one sample from the posterior and release this as the parameters, right? So if we got a lot of data, probably this posterior will be very concentrated around a parameter vector that gives you good predictions for the data. So with high probability, this one sample from the posterior will be a good parameter for making predictions on the model. So that kind of fits the Bayesian paradigm. And there are several results one can prove in this case by making assumptions about the prior and the likelihood or the model. And basically, you can apply this exponential mechanism of Minami Row. That's the 2016 paper, but before that, there was this one paper who are the ones who introduced this mechanism, the OPS, one posterior sample. And they basically showed that if the likelihood of your model is not too sensitive to changing one point in the data set, which is what makes sense, in the cases where it makes sense that you will be able to achieve differential privacy. So if this thing is uniformly bounded by epsilon half on the whole parameter space, then actually revealing one sample from the posterior is differentially private. And they call this privacy for free. Because if you note, there's nothing here about adding noise. You're just making an assumption about your model, the likelihood of your model, and if this assumption is satisfied, which is that the likelihood doesn't change too much when you change a point in the data, then taking one sample from the posterior is differentially private automatically. You didn't have to add any noise. But obviously, in a lot of cases, you cannot compute the posterior exactly. So in many cases, you have to do like approximate inference, like MCNC and all this kind of stuff. So this will affect your privacy guarantee because you will not be sampling from the posterior exactly. You'll be sampling from an approximation of the posterior. So you can look at these papers where they give like bounds in terms of like, for example, how many iterations or how close to convergence the MCMC is and how that will affect your privacy. And then there's obviously like if you're doing Bayesian machine learning, you can also do variational approaches, and there's this paper that does differential privacy for variational Bayes. And then there are like more like advanced or specialized algorithms for particular kinds of models like Bayesian networks. Yeah, sorry.
So is that kind of suggesting that if you have data and you can build a generative model that generates data that's indistinguishable from the original data, then this is like privacy for free?
Yes, that's, well, privacy for free. I don't know if that would fit exactly in the privacy for free, but there's people who are looking at this. I don't know the references out of the top of my mind, but I think what Thibault is suggesting is I could use this framework to learn a distribution of the training data, like not any parameter that predicts things about the data, but the data itself, and then sample things from this to synthesize a data set that looks like the original one, but is differentially private. But there's people who are looking at this. Yeah, you could do this, but I'm not sure you would find like a model that satisfies this, but there are like other tools you could use. Exactly, yeah. Yeah. This is kind of a generative adversarial network that learns the distribution in a differentially private way, and then like samples that you generate. And those are private for free in the sense of post-processing. Only the parameters of the network are differentially private, and you can release as many samples as you want. Okay, that's all I had to say about machine learning. Yeah.
So if we can do the differential private PCA, so after that we can apply any machine learning algorithm, so the result is differential private based on the post-processing property of differential private?
Yeah. Oh, sorry. So he's asking, if I take a data set and I process it in some way, like for example, I do PCA, and I make sure that the PCA is differentially private, is anything I do with this private projection of the data like private in the sense of I do machine learning on these PCA features? And that's the case, but there's a subtlety there, which is that sometimes you use PCA to compute a basis, so you can make the basis differentially private, but if you then project the points using the basis, the output is not differentially private again, because the basis is private, but you've touched the original data again to make the projection. So you have to be a bit careful on how you do it. Okay, so far I've been talking about epsilon differential privacy and epsilon delta differential privacy and how you can apply this to machine learning and other more basic data analysis problems. Now, one of the problems that happens when you want to do differential privacy, and this is very like obvious when you look at these proofs of these differentially private stochastic gradient descent algorithms, is that you need to apply composition a lot of times. And you have the composition theorem and the advanced composition, and these are kind of good, but they're still not optimal in some sense. So that's one of the reasons that has motivated people to look at other definitions of DP that have kind of better composition properties, and one of these is concentrated DP that I'm going to explain now. So let's introduce a bit more, some more notation. So recall that we have M is a randomized mechanism from X to Y, and the density of the output distribution of the mechanisms is P of Mx on a point Y. So with this, I'm going to define something that are the privacy losses, right? So we have a privacy loss function, which is just a likelihood, if you want, or a relative likelihood. So the privacy loss function of the mechanism X with respect to X and X prime on output Y is the logarithm of the ratio of these densities, the density of the mechanism on input X and the density of the mechanism on input X prime. So that basically measures how more likely is the output Y when I'm inputting X versus when I'm inputting X prime, or how less likely. Okay? Now, if I take this function and I stick a random variable in here, I'll get a new random variable. And when you stick a particular random variable here, you get the privacy loss random variable, which comes from sticking in Y a random variable that is the output of the mechanism on X. Okay? And that might seem a bit contrived, but one of the reasons why these things are formalized, and it's interesting, like if you look back at papers on differential privacy from like 2006, 2007, 2008, some of them were using these things, but they were not like definitions to be found anywhere. They were just things that were appearing in the proofs. But behind these definitions is this sufficient condition that says that you can guarantee that the mechanism is epsilon delta differentially private if you show that for any pair of neighboring data sets, this random variable will not be very big. So this privacy loss random variable will be larger than epsilon with probability less than delta. So if this is satisfied for every pair of neighboring data sets at X and X prime, this gives you differential privacy. And this is basically the idea behind the proof of the Gaussian mechanism. So let's try to walk through the proof. I promise you that, so here it is. Recall the setup. We have a mechanism. This is output perturbation with Gaussian noise. So we have an F that we're interested in computing and releasing privately. So we add some noise Z, and this Z is drawn from a normal distribution, a Gaussian distribution, with diagonal covariance with matrix with parameter sigma squared. And the sigma is the L2 sensitivity divided by epsilon times something that depends on delta. And by the way, I should mention that this only holds for epsilons bounded by something, and we're going to assume it's 1 in this proof. So this doesn't work for all epsilons. So now we can go to the objects in the previous slide and compute them for this mechanism, and something interesting is going to happen. I'm not going to ask you to guess. I'll show you. Okay, so we can compute the privacy loss function, right? So the Gaussian is something like e to the minus this thing divided by 2 sigma squared. So I have e to the minus this thing divided by e to the minus this thing and taking a log. So that's what I get. And then you can do a bit of algebra to simplify these square roots. And basically, because I want to compare these two guys, so you can expand these squares and put them back together again. And you get something that doesn't depend on y, plus something that depends on y. Okay? You can do this on the back of an envelope to convince yourselves. So now what you do is, I'm going to plug in y, so to compute the privacy loss random variable, I'm going to plug in y this distribution. Right? So this is the m of x, the thing I need to plug in there to compute the privacy loss random variable. So this f is going to cancel with this f, and I'm just going to get this thing, right? This thing doesn't change, doesn't depend on y, and here I cancel the f and I get the z. And z is a d-dimensional Gaussian, but when I take an inner product with something, I get a one-dimensional Gaussian. So this is Gaussian. This guy had mean 0, so that thing still has mean 0. So this is the mean. This is this guy here. And the variance is just this thing. And you can like basically do this calculation. It's basically what happens when you have an affine transformation of a Gaussian is again a Gaussian, and you have a formula for its expectation and its variance. Okay, so that's kind of interesting. So we have like the mean and the variance look the same except for a factor of 2. So let's synthesize this by saying that the privacy loss random variable of the Gaussian mechanism is a Gaussian that has with parameter eta and 2 eta. Okay, so now recall, I want to show that this mechanism is differentially private, and I want to use this sufficient condition that says that I want to show that this thing is small, less than epsilon, with high probability, probability 1 minus delta, or that it is bigger than epsilon with probability less than delta. But that's a Gaussian. So that's an interesting observation. The privacy loss of the Gaussian mechanism is a Gaussian itself. That doesn't happen for any other mechanism I'm aware of. But that means that to bound this probability, I can use concentration bounds for Gaussian random variables. So you go to your book on probability, you pick up one of these concentration bounds, and for example, you find out that with probability at least 1 minus delta, this Gaussian is going to be at most eta plus square root eta, and some constant and some log of 1 over delta. So what I have to show is that this is less than epsilon. If I pick eta such that this is less than epsilon, I'm in the condition of the, I'm under the assumption of that sufficient condition, and I've proved epsilon delta differential privacy for the Gaussian mechanism. So here is where your assumption that epsilon is small comes in. So basically, if you want to solve this thing, so you want to find an eta such that this is less than epsilon, you just do a bit of algebra, and you show that actually the eta that satisfies this is bounded by this thing squared. And then you do a Taylor approximation for small epsilons, and you show that this is less than epsilon squared. And then you substitute the definition of sigma star, I sigma squared. So eta is basically this mean here. So I substitute the mean here. Then I apply the expression for sigma star. So sigma squared. You can tell I do like language theory from time to time. So you get this expression, and here's where you use that this thing is a difference of f between two neighboring data points, and that's the supremum of this quantity over all neighboring x's. So these two things, like the ratio of these two things is at most 1. So I'm satisfying this thing, and therefore I'm epsilon delta differentially private. Now, why did I subject you to this pain? Why did I have to go through this proof? Well, first, to show that this notion of privacy loss random variable is useful to get proofs of differential privacy, especially epsilon delta differential privacy, and actually like most proofs that establish epsilon delta differential privacy, the delta either comes from a concentration property or from an advanced composition. And second, because this concentration property that appears in that sufficient condition is what is used to define these alternative notions of differential privacy that are concentrated differential privacy. So these notions basically follow this paradigm that they say differential privacy is really a concentration property. So what does that mean? That means that if I have a mechanism, a randomized mechanism, and I have its privacy loss random variable, well, you have different ways to measure how concentrated a random variable is. One of them is to look at its moment generating function. Right? So the moment generating function is without this log here, is the expectation of e to the s times the random variable. Right? And this s is a real number. And when you take the log of these instead of the moment generating function, you get the cumulant generating function. So let's call this thing the cumulant generating function of the privacy laws random variable of a mechanism the cumulative generating function of the mechanism. Doesn't make any sense, but humor me. So using this phi, this cumulative generating function, you can go then in the literature and find 3 different variations on the notion of differential privacy. There are concentrated differential privacy, zero concentrated differential privacy, and Renyi differential privacy. They're all the same. when you look at them from the right point of view, right? So, and what they basically say is that you want this phi to satisfy some bound, right? And because phi is a summary of, or is equivalent to the distribution of the privacy laws, these bounds imply concentration properties. And like everyone working in machine learning that has done some concentration inequalities will know this, and any computer scientist that has seen like the Chernoff bound will know about this. So that's kind of very well known. So concentrated DP, for example, it says that mechanism will be mu tau CDP, concentrated DP, if for all pairs of neighboring data sets and for all s's bigger than 0, you have this bound on the cumulative generating function, right? So it's like a linear term and a quadratic term. Zero concentrated DP is just a slight reparameterization of this. Now the parameters are psi and rho, and instead of putting mu here, I put psi and rho, and I put rho here, so the linear and the quadratic term are kind of coupled through rho. But it's basically the same thing. And then you have Renyi differential privacy, which is slightly different because Renyi differential, so note that these two things are kind of give me like parametric bounds on the phi, because this thing has to be satisfied for all s. It basically says that I have this upper bound on phi for all s. Renyi differential privacy instead just says, I will look at one point of this phi. So I will say that the mechanism is alpha plus 1, and that's to make the notation fit with what's in here. Alpha plus 1 beta Renyi differentially private. If for all neighboring data sets, the cumulative generating function at the point alpha is bounded by alpha times beta. But they're all the same. So why is this interesting? Well, this, first, it abstracts something that is kind of at the heart of this proof that I gave you for the privacy of the Gaussian mechanism. So if you look back, you'll remember that the privacy laws random variable of the Gaussian mechanism is a normal with mean eta and variance to eta, which basically means that the cumulative generating function is s eta plus s squared eta, right? So if you go here, for example, you'll see that if you say set psi to 0, this is exactly this form. So this thing is 0 eta, 0 concentrated differential privacy. So basically, the idea is that these definitions try to abstract this concentration that we applied to prove that the Gaussian mechanism is differential private, to basically say things just about this cumulative generating function. And you can always go back to epsilon delta dp. So again, if you've proved any concentration bound before, you'll know that you can, when you have like a bound on your cumulative generating function, you can use Markov's inequality to show that, for example, if you have an S such that for any data set, the cumulative generating function at S plus log 1 over delta is less than S epsilon, then the random variable, the privacy loss random variable, is at most epsilon, is more than epsilon with probability less than delta. So the sufficient condition gives you epsilon delta dp. So you can always go from concentrated to the approximate differential privacy. So these are the two things that motivate this thing. And one of its most important properties of these definitions is that in here, the composition is exact. You lose nothing by doing composition when you're working with cumulative generating functions. And that's what this says. It basically says that if you have a bunch of mechanisms, mi, and each one of them has cumulative generating function phi I, and you look at the composition, so you apply m1 up to mk on the same data set, then the cumulative generating function of m is exactly, so there's no inequality here, is the sum of these guys. So you can control exactly how these things accumulate. And that's the idea behind this moment accountant that was used to like get an algorithm for doing differentially private deep learning with good accuracy. Is to say, well, instead of like applying composition at every time I touch the data at the epsilon delta dp level, I'll look at these functions and I'll aggregate them exactly, and then I will apply this at the end. And that gives you like better control on the final privacy guarantees than just applying advanced composition over and over. Okay. Now I want to move to another variant of differential privacy, which has a completely different motivation. And I won't say much about it because it can get really technical, but I think it's good that you see the idea, because it's actually like where things like randomized response make sense, and that will explain where this assumption of the curator helps us or hurts us.
One question regarding the previous. So are there other applications of this that don't have to do with composition? Generally, just a way of handling?
I think the main motivation for me is composition. I mean, if you look at the original papers, they show that these things have all the properties that also differential privacy has. So you could basically work with these bounds, but actually I think like the interesting thing would be just to work with cumulant generating functions like forever, because you have this property. And then if you want to say, well, I can give you the cumulant generating function, that's the privacy guarantee, but if you don't understand that, I can translate it into like point-wise bounds.
Okay, so we can think of this as advanced composition.
Yeah. Okay, so what's wrong, or what are the issues with this trusted curated assumption that I've been using, especially when I was talking about all this differentially private machine learning? Well, there are several issues in my opinion. One is that this introduces a single point of failure, right? So there's one curator that has the data about everyone. So even if this curator implements differential privacy correctly and releases something differential privacy and is completely ethical and follows the rules and everything, they might be subject to other security vulnerabilities, right? Like some hacker could like penetrate their network and leak the data set. And then it doesn't matter that you're doing differential privacy or whatever, like all the information is leaked, like everyone loses their privacy. So the trusted curated assumption is a single point of failure, and that's something that you might want to think about, especially when you're talking about like super sensitive data. Another thing that might happen is that the curator might not really be trustworthy, especially when they are tasked with collecting or keeping very valuable data, right? So if the data is very valuable, the curator might have incentives to misbehave and sell it in plain text as opposed to applying DP. So the more valuable the data gets, the less incentives there might be for somebody to act as a trusted curator, assuming they're not afraid of you suing them. And finally, I mean, it has to be trusted by everyone, and that might be a problem in itself. So it requires an agreement, and the more people that need to agree on something, you know, like that generates more and more arguments. So it might be hard to find somebody that everyone in large population trusts enough so that they are happy with them handling their private data. So these are just some of the issues that the trusted curator assumption has. So that raises the question, can we do differential privacy without the trusted curator? And I've already shown you we can. And this is the example of randomized response. So in randomized response, there wasn't a trusted curator. There was a set of inputs, like whether you like Justin Bieber or not. And for each of those, everyone, before answering the survey, randomized. So the person who was collecting the answers of the survey didn't really see the true answers, wasn't a curator really. So that's an example of local or multi-party differential privacy, right? And that's the last model I want to introduce. So in this model, things are slightly different. So there's still a data set X, but this data set is distributed among m parties. Okay, so we say that party I owns this xi. Okay, and that M might be n, so that everyone has their own data. But you can also think that M is like small curators that a subset of the population trusts. Right? So this could be like several hospitals, and everyone has data of their patients, and the patients trust their hospital, but they might not trust like other hospitals in other countries, for example. So then, if you want to analyze this data using differentially private, the setup that you usually use is the following. So there's going to be an analyst that's going to initiate a randomized protocol, pi. Right? So pi is going to look at the whole data set, not directly, but through talking to the parties, and it's going to output a y. Right? So this will require interaction between the parties and the analyst. And then if we want to formalize what are the privacy guarantees that we can expect from pi, what we can do is we can say, well, like, let's look at party I, and let's look at all the messages that leave from party I that depend on the data that party I has. So let's call this a mechanism, mi, that depends on xi. And know that mi can also depend on the data of the other parties that the analyst received and used to say, well, party I, tell me this thing about your record. But we want to see what happens at these outputs generated by party xi, by party I, when party xi is trying to protect their own data, when things about xi might change. So what we say is that this protocol pi is multi-party epsilon delta dp if each of these individual mechanisms that generate all the outputs from the party I are epsilon delta dp. And yeah, I already said that when each xi has size 1, we talk about local differential privacy, but in general, multi-party is a wider definition. And randomized response is an example of how to implement this, and it's also an example of something that is kind of fundamental between the curator setting and the distributed setting, which is that you will lose utility. There's a lower bound that tells you that you will lose utility. And the paradigmatic example is like I showed before, the error, for example, when you're computing means in terms of the number of examples. So in the curator case, for example, when we can apply Laplace, the error is going to be 1 over n, and in randomized response is going to be 1 over square root n. And that's a fundamental restriction of local differential privacy. Okay.
So fundamental in the sense that there is no algorithm that will give you better utility in the local model?
Yeah, in the sense that there's a lower bound on the utility for a fixed privacy or for a range of privacy parameters that has this asymptotic behavior. Okay, the worst is over, no more math. So I'm just going to do some final remarks, and I would like to start by saying all the stuff that I didn't include in the tutorial that I think is important, or that I think that is worth looking at as part of the foundations of differential privacy. So there are many basic mechanisms I didn't cover, especially things that are about selecting the maximum in the data set in a differentially private case, selecting the top k satisfying differential privacy, and other private data structures that have privacy embedded in it. This is a big topic. I think it's very relevant, and it's necessary if you want to build advanced mechanisms. But it kind of falls more into the database space than ML space. So that's why I didn't include it here. There are many general theorems that I didn't cover. So I explained the properties of advanced composition, group privacy, robustness to adversaries, but there's other things. So there's results that say that essentially everything is randomized response in a very ambiguous way that I'll leave ambiguous. There are several lower bounds on the utility telling you cannot get more utility or more accuracy than this if you require this amount of privacy. And this thing about local DP is one of these examples. There are also hardness results on the computational aspect, saying that there are things that are hard to make differentially private in a computational sense. There's also a field of a part of differential privacy that is about designing optimal mechanisms. I have this problem, how do I design the mechanism that has the best utility for this problem? There's quite some work there. And from the machine learning point of view, there's also connections to generalization, because differentially private algorithms, by definition, are quite stable to changes in the data. And when you're stable, you generalize well to future data. And there are very precise results that exploit this connection. There's also the database perspective. In the database perspective, you think of differential privacy in a kind of interactive setting, where the curator offers you kind of an API, and people keep answering questions about asking questions about the data, and you want to keep responding. And if you do this in a naive way, you'll apply, for example, advanced composition, and at some point, you'll have to say, I cannot answer more questions, because if I keep answering, I will be beyond my privacy budget that was epsilon. So there's quite a lot of research into looking at how you can beat this advanced composition and even beat what the composition in concentrated differential privacy gives you when you're focusing on particular families of queries. So that falls into this category. And in this case, there's also a distinction between if the attacker makes adaptive queries or non-adaptive queries. Then there's another line of research that's also quite interesting, which is what happens when this global sensitivity is too pessimistic, is atypical. And this gives rise to other notions of sensitivity or other models of privacy where you can get away with adding less noise when the data set is kind of typical. It's not the worst case data set. So that's like the smooth sensitivity or randomized DP, where you assume that the data comes from a distribution as opposed to being worst case. And then there's many other variants of the definition. I gave you like concentrated DP and local DP, multi-party DP, but there's also like things that are specific to location data. There's things about like what happens when the data arrives in a stream and you're continually releasing things. There's more abstract definitions that have differential privacy as a particular example. So I think all these things are worth looking at, and like my two go-to readings for like getting into this space are the book by Dwork and Roth, and these lecture notes by Badan, which are like both very, very good references and contain a lot of material and plenty of more pointers to more papers you can read. So that's what's out there. What is not out there? What's missing? What are open research challenges? And that's a very like personal choice. Like there's many things one can look at. Things that I think that are very interesting to look at this moment are one topic that I call bounds versus algorithms. So I showed you that how you calibrate the noise if you have Laplace noise, like Gaussian noise. I told you like how you do the calibration when you have exponential mechanisms. But few of these analyses are tight. Only randomized response, Laplace, and the epsilon DP exponential mechanism are tight in the sense that if you have the exact global sensitivity, these give you like the exact variance that you need to satisfy this and not more. But there are many other cases where the analyses are off, and they can be off by constants, they can be off by worse things than constants. But in many cases, they're off by a constant at least. So these constants matter because they tell you how much noise you need to add. So if your constant is off, you're adding too much noise for your privacy requirements, so you're hurting your utility more than you should. So, and the problem is that in many cases, these mechanisms are so complex that like doing a tight analysis by hand might be, well, impossible, or might be like, you might require unreasonable amounts of time. So one thing you can do is try to instead calibrate noise using numerical computations. Like for example, you can try to get the density function of your distribution and do these computations that you do in the proofs, but numerically, and hope to get like better bounds or at least better constants. So challenges for this are, well, like moving away from concentration bounds and using exact densities, how you deal with different types of compositions optimally. Things like subsampling and other mixtures are hard to like get like tight results for. And then there's all this business of approximate sampling when you do like Bayesian differential privacy machine learning, for example. Another line of work that I think is kind of open is all this issue of like the correctness of implementations of differential privacy and attacks to test this. So I made the remark at the beginning that because this definition has a couple of for-alls, it's not possible to test empirically if something is DP or it is not. Or at least like nobody knows how to do it, to the best of my knowledge. So we have to resort to mathematical proofs, and maybe this can be automated. And that's a line of research that like the programming language people are already exploring. They come up with small programming languages that allow you to code differentially private algorithms, and then you can provide the proof in this language, and you can automatically verify that the algorithm is correct. But that, I mean, is okay for small like pieces, but sometimes composing these like for big systems might be beyond the reach of the current tools. So other things that we have to try is to actually like break DP. So even if we cannot verify that something is DP, we can have an attack that tells you that it is not. And that's an interesting line of work, because these attacks will have to be specific to the task you're at hand. So the DP guarantee is very abstract, and that makes it very nice. But also, like, it's different what the guarantee means when your output is a vector of parameters of a logistic regression versus when the output is the average of the salaries of people in a data set. So if we come up with attacks for DP, that will help us better understand what epsilon means in different applications, and will also help us find potential flaws in DP implementations. And so the biggest challenge here for me is that moving from pseudocode to implementations, many things can go wrong. For example, like when we do the proofs, we assume that our x's and y's are real numbers, but computers work with floating point, and that's already been used to showcase some attacks on differential privacy. So that's another important line of research, in my opinion. Okay, finally, the conclusion slide. I hope I've made the point that differential privacy provides a formal notion of privacy with many desirable properties. In particular, and I want to emphasize this again, we have a precise way to quantify the privacy utility trade-off. Differential privacy is robust against adversaries that have side knowledge, which is a very strong assumption on what an adversary can do. And they can be this definition can be applied to a wide range of data analysis problems. Maybe it doesn't solve everything, but I think it's a good start. There's also it's already, like, even after like 12 years, it's already a quite mature field of research. So we have a rich toolbox of mechanism design strategies, like Bayes mechanisms and how to combine them. So I think that shows that this is an important definition and something to look at if you consider like working on privacy at all. But obviously, that doesn't solve every single problem related to privacy. So it might be that differential privacy is more a natural starting point for application-specific privacy guarantees, which I hope would have like a similar flavor of at least like compositionality and robustness to post-processing and robustness to adversaries and so on. And actually, there are already several real-world deployments and open-source tools that you can find out there. So, for example, Chrome has a plugin called Rapport that lets you like provide feedback to Google using local differential privacy about which websites you visit. The iOS 10 released by Apple also has some local DP in there where you send feedback to Apple, for example, about which words you're typing so that they can detect new words or like patterns of words that people commonly use without seeing which word you're using precisely. The US Census Bureau is also using differential privacy to release, I think, some location data. And there are like at least 3 systems I'm aware of that are released as open source: GAPT, Microsoft Ping, and Uber's Flex that was released last year. That's all. Thank you.